Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In the given parallel plate capacitor, which has circular plates of radius 40 millimeter and is being discharged by a current of about 6 amperes. So let's begin by drawing a parallel plate capacitor. Imagine that these are the circular plates of a parallel plate capacitor. We need to find the magnetic field which is induced is equal to 75% of its value, that is the maximum value, both inside and outside the capacitor. So we first begin by the net current I. The net current I in this case, and we should remember one thing, that this entire current is spread across the entire area of our plates. So the current on any particular section, so this current is actually defined as what we is now the current density J into the entire area. So the entire area of this parallel plate is pi into the radius, which is r square. So this is pi r square is the area, and this is the current per unit area in our case. So the current at any given radius r, suppose we take a small radius r, the net current which is there inside this radius will be given as this value J into pi small r square. And thus we can write the whole thing as capital I r square over capital R square, where I is the total current over the entire surface. So we notice one thing, that as the radius I increases, the total current, as the radius r increases, the total current over the area which we have bounded within this radius keeps increasing. It from at r. Beyond this, because beyond this we do not have any plate, the area, the current I remains constant, which is the maximum current. Now we invoke Ampere's law, which goes as B dot dl is equal to mu naught I, where I is the net current which is enclosed within the loop. So we make a loop, which is our Amperean loop. Imagine we make a loop. So instead of drawing here, we can draw here a loop which has a radius of all r, and this closed integral says that this is an entire loop which has to be closed. This is the loop element. This is a magnetic field. So magnetic field in this case at a radius r is now defined as mu naught I. So we substitute for I from here, which is r square over small r square, capital R square, divided by the entire loop dl. So dl is the line element, so we have the entire loop which is the perimeter of this, so that's equal to 2 I and small r. And now we see that the formula, so we'll just limit this right now. Now let's start with the A section. So section A, we need to find out the radius which is internal inside this, at which the magnetic field is 75%. The maximum occurs when small r, because at that point we have the total current I, which is equal to small I. So we can also write what is P max. So P max is equal to mu naught. As I said, it should be capital I, because that is when small r is equal to capital R, divided by 2 pi r. Oh, sorry, because the two r's are same exactly. We need to find the 75%. So 75% is 0.75, 0.75 of these two. The ratio of these two is 0.75, and that is mu naught, I and I gets cancelled out. So I can see straight away write this as r square over r square divided by 2 pi r and 2 pi r. That gives us r over small r is equal to 0.75, or r is equal to, so the first look at which the magnetic field is the maximum is 3/4 of the entire radius. Because we have a radius of 40 millimeter, this is equal to 30 millimeters. Now we look at the second case. In the second case, we again need the 75%, but this time it will be outside. We need to take care of one thing here, and that is this factor remains same because it's the maximum value, while this changes. Now, as R increases, we have to take one thing, that the current cannot actually increase. If I make a radius somewhere here, which is outside and which is what we need to calculate now, current which is enclosed within this loop is still going to be the same. It's not going to change now. So this value is going to be I for us, which is the maximum I, the maximum current which can actually flow. We can go further and further away, make further and further loops, but the plate is constant, the size and the overall current is still the same. This is equal to gets cancelled out, and we have simply a value of capital R over small r. We can see from the entire expression, so we have a capital R over small r, and that actually gives us, where this r, remember one thing, this r is greater than r, so I should also write that this is when r is actually, that doesn't look like a good r, this r is actually greater than the capital R. And so all of this happens when r is exactly equal to a third of our capital R. So this is equal to 4 by third. There it was 3 by 4, now it is 4 by third of capital R. And thus it is equal to, if it is 40 millimeters, this whole thing now becomes 53 millimeters. We go back to C. So the problem C tells us that we need to ask us to find the overall maximum magnetic field, that is B max. As we said previously, B max is equal to mu naught I over 2 pi r. I is 6 amperes, R is 50. When we substitute these values, we get a value of T into 10 power minus 5 Tesla.